So I'd like to thank Andrew and his team for inviting me to speak this afternoon, and also thank all of you for coming to listen. So I'm going to talk about the water cycle, and hopefully you will have all availed yourself of some of that resource during the break in an attempt to cool down. I'm just wondering as well, because some of these slides I put together to work with another group of schools, but they were concentrating on delivering the EdXL curriculum. Is anybody doing that one here? So on some of the slides you'll see some numbers on the top, so you'll get the slide pack afterwards, and that relates to the numbers in that specification for that exam board, so hopefully that'll be useful. I've put together a fairly broad range of things, and also put a few slides together at the end about the research I do, which might give you some ideas for kind of case studies and things, and how some of the kind of research is being applied. I'm also quite pleased that I'm following waste and not beaches, because I think that probably tempers some of my slides a little as well, hopefully. So I'm going to cover material on the water cycle. We're going to look at water stress, water security. We're going to look at projecting water availability in the future. We're going to look at solutions for dealing with water scarcity in future. And we're also going to look at how water links to other themes as well. And as I've already mentioned as well, put a little bit on my water-related research in there. So by background, I'm a hydrogeologist. I've spent quite a lot of time looking at water that comes out of the ground, drilling holes to get water out of the ground, and more difficultly trying to get water to go back into the ground as well. So we'll have a whole range of things related, water-related. So I haven't, I wasn't planning to prepare too much on the actual what's in this diagram, because you'll know probably far more than I about much of what is in there. But that said, we've talked about the fact that we're going to develop some kind of resources alongside some of the presentations. So I've put together an exercise that you might want to do with your students on the water cycle to make them think about where water is stored and how it moves between the stores, which I think, having looked at some of the specifications, that seems to be one of the key things I need to think about. So I put together a little worksheet which I'll send out with the materials afterwards, where you get the students to produce a table with all of the non-italic numbers in, i.e. they're putting the quantity for each reservoir into a table. So they'll do that, and then they'll work out the relative percentages of each, and then get them to repeat the process again, but leaving out the saline water. So we're looking at what's fresh water, what's potentially available for use. When you've got them to do that, then this is hopefully what your students will have done. They'll have derived the first two columns on that diagram there, and by doing that as well, they should have developed an appreciation of relatively how little of the water on Earth is fresh water, and then within that, how little of that is actually available for us to use. So from there, in the middle diagram, we've got groundwater is kind of what's accessible to us to use, as well as the very small proportion that comes from fresh water sources. And there's been some recent research, which I'll show you in a minute, which is quite a good paper. It's got some good diagrams in. I've got the reference for it in here, where they've tried to quantify how much is that 30% of groundwater that we have that's accessible to us. And it works out at a volume of something like 23 million cubic kilometres. So if that was to be spread over the entire land surface of the Earth, you're looking at a resource that is as deep as the height of the Gherkin in London, just to put it into context kind of for your students. Of that 30% there is quite a small portion of that is accessible to us for reasons which we'll go into in a bit as well. So of that 30%, again, we can still only use a small portion of that. So hopefully your exercise that you'll do with the students, if you decide to use it, will enable them to define both of these two things and work out for themselves the relative importance of some of these stores. And then you can take that one step further by looking at the third column and drilling down into some of the kind of facts and figures there, if they're interested in doing that too. And also something else to think about is how long the water spends in each particular area, and perhaps you might want them to think about why that's important as well. So in that table we've got the kind of places where water sits around for the longest time at the top of the table, where it is cycling more frequently at the bottom of the table. So we may want to think about the fact that if water's somewhere for a long time, there's a potential for it to accumulate things possibly. If water is being cycled on a short time scale, we're interacting with it a lot, so we need to be sure of what the quality is and how sustainable is that resource. So there's lots of things to think about there in terms of how long water is spending in each different part of the water cycle. And by doing that exercise, one of the things the students hopefully will have picked up on is the importance of groundwater. So they can have a think about that in, if you pardon the pun, in more depth. So we can think about the shallower groundwater and also deeper groundwater, which is confined between other layers deeper in the earth. And the reason we want to think about that relates to this research that I was talking about. So a recent attempt to quantify the volume of groundwater that's available to us. And you can see it in the top diagram. It's kind of the blobs are comparing the relative quantities. And then what they've done in the paper is they wanted to work out how much of that was what they refer to as recent groundwater. So groundwater that's probably around about 50 years old. And the way they did that was they looked for the presence of the radioactive isotope tritium, which became common. Well, it peaked in rainfall concentrations in the 1950s because of above ground nuclear testing that was going on. So they were able to use that as a marker, and they found if that was present, then they were saying that water was 50 years or younger, and if it wasn't there, then it was likely to be older than 50 years. So that's how they approached this. And then from that, they were able to work out that only a small proportion is this what they call young groundwater or modern groundwater, less than or up to 50 years old, and that relates to about 6% of that total amount of groundwater that was defined in the first place. So of all the groundwater that's there, 6% of it is what we call recent or modern groundwater. And why is that important? That's important because it's what we interact with most frequently. It may be a more renewable and sustainable resource because it is cycling through the water cycle more quickly. So we interact with it. It's strongly coupled with a hydrologic cycle, which is good because of the frequency of which it's cycling and how many times we can use it and access it, but potentially bad because it has the potential to be affected by contaminants or pollutants. And also because it's relatively shallow, again, we have to be careful that it's adequately protected so that it can be used and not be contaminated. And the really key point here is that globally, more than 2 billion people rely on groundwater as their primary source of water. So hopefully by the time the students have gone through that exercise, they'll have a feeling of how important groundwater is as a global water resource. So I'm going to move on now to look at what happens when there's not enough water. So we're thinking about globally how water is used, and generally most of it will not surprise you that it's used in the agricultural sector. The next biggest user is industry, and the smaller portion at 8% is what we're kind of using in our households for domestic purposes. So there's things here for the students to think about in terms of future. How do we secure future resource? Where do we tackle our efforts in order to reduce water use? So you can see that by making very small savings in the agricultural sector, you have you're protecting larger volumes. So it would maybe be something you could get the students to think about. Where should we direct efforts to manage water consumption going forwards? So this is a graph here which shows water scarcity, and you'll see from there some interesting places that the students could maybe pick up on and question why places are coloured red, why places are coloured blue. The UK is verging on vulnerability because of our population. And because relative to some of our European neighbours we receive less rainfall, I think London receives less rainfall currently than Istanbul, so it just puts it into perspective. So you can get the students to maybe pick some countries. I put another kind of resource together where I'd listed pick some countries at random. They could have a look on the map, find out what status they were with respect to water scarcity, and do some problems around that, and thinking about future water provision as well. What might happen if populations change? How able are certain countries to buy in water from other areas, either in the food that they buy in or by physically buying water from other countries? So all those kind of conversations could kind of stem from looking at a map such as this. And then we're thinking about the causes of water insecurity. So basically there's a kind of average demand, and the average demand is in this bracket here. So that's the kind of average. So that on the slide I've got, it kind of comes up as a yellowy green. All those three in the middle look quite similar, but you'll actually see from the slides that there's kind of a fairly distinct band in the middle, which is the average one. So again, you can look at who has the kind of below average consumption and who has the more kind of the higher than average consumption. So you could look at outliers again on this map. So perhaps you could home in on Mongolia and think, well, why do they use so much water? They have a high reliance. I think 80% of their water comes from groundwater. They're developing, and one way in which they're developing is there's a lot of mining going on, and the mining industry accounts for a lot of water use in that country. So you could get the students to kind of pick some of these outliers and think about, why is there a green area next to two red areas? Why is a red area in the middle of areas where it's green? So there's quite a few things they can do there. And then also they can build on that too and take it down to a more personal level and think about how much water they're actually using. So one thing perhaps you could get them to do would be to get them to keep a water diary over the weekend or over 24 hours and get them to think about how much water they've used. So you would hope in that time period some of them had taken a bath or a shower, they'd maybe been to the loo, they'd had a few cups of tea. So you get them to list that and work out how much they actually consume in terms of what they're physically using to wash themselves, to drink, to cook their food in. And that, on average, works out at about 150 litres per person. But then if you get them to do the same exercise again and actually list the foods that they've had, then and look at the water that's embodied in those foods, then you can soon ramp up that personal water demand quite considerably. And also, again, if you build into the clothing that they're wearing as well, they can look at how much water is embodied in the clothes. So cotton, for example, has a really high embodied water content. So jeans, t-shirts, a lot of the cotton may be produced places like Kazakhstan, well known for growing cotton, and the impact on water resources for cotton production there has been the reduction in size of the Aral Sea. So you can have a look at kind of imagery which shows how that's shrunk over time. So that'd be something for the students to connect across. The size of the Aral Sea, which is where they've been supplying the cotton growing, where they've been irrigating using that source. So if we have this kind of 150 litres that we kind of interact with, and we're using that in terms of showering, making cups of tea during the day, by the time we add in the embodied water, then for an average person, then it's around about 3,500 litres, which is equivalent to about 15 baths full, and that's daily consumption, including everything embodied in what we're eating and drinking. So obviously diet is a big portion of this, so you can look at different countries and compare different diets and see what effect that has on embodied water. Meat consumes a lot of water. I'm lucky, I live somewhere where I can grow my own roast dinner and farm my own roast dinner, but because it's quite rainy where I live, I don't feel that I put a lot of water into that, but then it's not without its own efforts. but they can think about what they're eating and where it's coming from and how much water it embodies and what impact that's having. And they can also look at places perhaps like Qatar, who don't have a water resource, but because they're an oil producing nation, they can afford to buy water in terms of buying in products that contain it already, and they can also afford to desalinate seawater. So there's quite a few interesting things they can do there to look at demands and compare them across different countries and just between each other. Perhaps if you've got students that are vegetarian, they could compare their intake with students that have a non-vegetarian diet. So we're going to have a look at future and what the future holds for us in terms of water. So perhaps we're quite afraid, perhaps we're all doomed. Looking at the maps and the graphs there, currently we are, this 2005 figure shows that supply is slightly shorter than what we're demanding. So when we project that going forwards to 2030, it works out that about 60% of the population will not have the water they require. And in areas that are already facing water stress, such as China, India and South Africa, then those areas, maybe 50% will not have the water they require. So there's something for the students to think about here going forwards in how we can meet that gap. What technologies can we use to do that? So they could do some research to find out what technologies are being used. And they could also have a look at the kind of future projections for water stress and compare those to the graph we were looking at before, which is a snapshot of what's happening more or less now. Look at future projections, see which countries have changed. So are those countries that are developing, what procedures and practices are they doing that are making their water consumption change? Is it somewhere that's having a big population growth? So there's lots of things again that they can look at there and comparing what's happening now with future projections. There's quite a lot of data out there as well, so more opportunities for students to prepare graphs, handle numbers and kind of do analysis of data. And to use London as a case study, so at the moment there's a problem. We have a shortfall of 133 million litres per day, and things are only going to get worse. So by 2040, that has quadrupled to 414 million litres per day. So what does that mean in terms of people that don't have water? That's 2 million people in London without their water supply at that time. So Thames Water are developing some strategies to try and get around this. So they're looking at the potential of putting in reservoirs, but then there's whole issues of where do we put them, land availability, planning requirements. They've hit a lot of barriers with planning where they're wanting to put reservoirs. They've also been looking at desalination. So since 2010, London has been running a desalination plant from the Thames. So that's already taking place to meet the high demand in the summer periods when there's least rainfall. And another thing they're looking at as well is they've trialled aquifer storage and recovery. So the reason I was showing you that picture of the groundwater kind of cutaway diagram before was so that you could think about the deeper groundwater levels that I showed you trapped beneath confining layers of rock. What they're doing there is when it rains, they're taking some of the surface water and they're putting that underground and then taking it back out again at times of need. So that's a research area that I'm particularly interested in. I've got a slide on that to talk a little bit more about that later. So there's various options they're working through, but often when you think of desalination you think of that taking place in hot countries, but it's been going on here since 2010. So we're thinking about water security and not wishing to put anybody on the spot, but is anybody willing to shout out a cause of water security issues? Anybody got? Conflict. Yeah.
Climate change.
Yeah.
Increasing demand for meat.
Mm-hmm.
Old quotas, meaning you're taking more than you should have had. Thinking
Yeah.
of this.
Okay.
Riparian rights.
Yep. So there's a whole load of things that you can think of. So perhaps the students could do a similar task and shout out what they think. Some of the things that I've picked on, some of which have come up. And again, these were linked into the EdXL syllabus as well, which is why I've kind of chosen these ones in particular as well. So climate change is in there, saltwater intrusion, overuse and over-abstraction, and also impacts of pollution. So I've got some material in each of those. So what's going to happen in a changing climate to our water supply? So potentially we've got melting of polar ice. So water which was fresh water bound up as ice may be melting into the ocean. Now it's become saline, and that in turn is then going to affect ocean composition, ocean circulation. There's an increased amount of water in the atmosphere, so the whole water cycle processes may be happening more quickly and more intensely. In some areas, precipitation may be rainfall rather than snowfall. Inland, you may have a scenario where you've got melting of glaciers, and that may cause problems when all that ice has melted. You've got a kind of resource going whilst that melting is taking place, but once that process is complete, any rivers, streams, lakes fed by that source may struggle to kind of keep supply. And then you've also got potential for reduced rainfall in the subtropic areas. So again, the key message is that the water cycle processes will become more intense and possibly speed up. So saline intrusion is also a problem. It's a naturally occurring phenomenon which occurs around the coast, and basically it's caused by an interface between the seawater and the groundwater. So the seawater, being more dense, pushes underneath as a kind of tongue underneath the fresh water. So you can see that can obviously, that situation can remain like that until you get to the point where you're taking out more fresh water than is being replaced. So effectively you're reducing the depth of fresh water, which means that seawater tongue is coming further and further inland. And by coming further and further inland, the interface is moving up, and you could imagine that if you had a well where that kind of vertical line is now, you'd start to see saline water breaking through as that pushed inland. And it affects many countries, so examples are Pakistan, India, Tunisia, Cyprus, Morocco, and also the southeast coast of the UK. We've over-abstracted heavily from our chalk aquifers down there. Consequently, some of those wells are now saline. And the key thing about it is that it's more or less irreversible. So once you have saline water at your well, it's very difficult to then go back to making that well supply fresh water. So here there's a clear link between the need for management and knowing exactly how much you're taking from a certain source, how much is sustainable. So there's lots of instances of infrastructure problems caused by over-abstraction as well. So this example from Mexico City, and I think in about the 1850s, they found a spring source beneath Mexico City that could supply about 3/4 of the water for the area. So this is a city with a population of 20 million or so, growing at around 350,000 per year. And so in the 1850s they thought, great, this is a great source of water, we'll use this, and they pumped it to feed the growing city, and the result of that has been that over that kind of period of 100 years, between 1850 and 1950, the substance realised in the area was about 9 metres. And so it took them 100 years to work out, make the link really between the over-abstraction of groundwater and the substance that was going on. And so the upshot of that was, at that time in 1950, pumping from the central part of the city was banned and moved to the periphery. So that meant that the central part did stabilise, but in the outlying areas there's still subsidence going on. And this statue that was built in 1910, that didn't subside, but unfortunately the land round it did, to the extent where they needed 23 new steps to be able to get up to it. So it's, and that's the kind of least of your worries because of the other impacts it's had on buildings, rail infrastructure. There's problems with it in China. There's a paper just come out looking at the effect on rail networks in China for high-speed trains. They run at 350 kilometres per hour, and over a 100-metre stretch of rail, you can't have a dip of more than 26 millimetres. So when you've got areas that are moving on the scale of maybe 2 or 3 centimetres per year because of groundwater abstractions, it's pretty hard to keep those areas within tolerance. So they're actually looking at routing railways around certain parts of aquifers which are less compressible for that reason. So there's quite a few places where this is going on, so there are quite a few case studies out there. I just wanted to put this one on because I thought it was quite interesting the way the monument hadn't moved and things have. Other impacts as well. So out to the east there's this lake, and that lake now sits 1.8 metres above the city. So you can see also things like flood risk are increased as well. And once you've got the water out of the city, out of the system, it's very difficult to get it back in as well. So once you've removed that water, it's really hard to kind of repressurise that aquifer to get it back in.
Can I ask why the monument hadn't subsided?
I think it was overlying bits of the aquifer where, so basically they're abstracting from a deep confined aquifer, and that wasn't beneath that, so there's like a tongue where that wasn't beneath it. So that bit was kind of preserved and everything around it sunk down. So I think they were just lucky, really.
Excuse me, what's the name of the lake that we've just been talking about?
So it's Lake. Hang on, I've got it on the bottom of my thing. I think it's Lake Takoko. Is it Takoko? I think. It's in my. It is in the bottom of my slides. But it's that's 1.8 metres now above the level of the city. So some of the other things, I'm not going to go into each of these because again you're probably well aware of a lot of them, but just point out some of the kind of new research on some of these themes. So on a module I deliver on Water Worlds, the students were quite interested on the theme of microplastics. There's not a lot of new research on that. So there's kind of basically two kinds of microplastics. One that comes from big plastic that's just been persistent in the environment and broken down into small bits, and the other type is plastics that were intended to be small and made to be small in the first place. So here we're thinking of toothpaste, various cosmetics, any cosmetics that have a kind of abrasive bead in them, they're often plastic. So there's a campaign, you can put an app on your phone, you can scan products when you're buying them now to see whether they contain microbeads, called Ban the Bead. And the reason microplastics are a problem is they're very good at attracting unwanted things. And by that I mean kind of organic contaminants or metals. So they can become concentrated in undesirable elements, and then because they're small, they're consumed by things which then get into the food chain. So you could get the students to maybe think about that, think about what the sources are, where they might be found, where plastics end up when they use products. Things go down the drain, where does that ultimately end up and what does that mean? We can think about thermal pollution, so I'll talk a bit more about that in a bit. So I've got some more related stuff on that. Obviously all the kind of pesticides, herbicides used in agriculture. If we are to feed growing populations, we want our land to do more. So there's more emphasis on getting higher yields off less area. So there's greater potential for there to be more of these kind of pesticides in the environment because more may be used. And the key message as well is that a major issue globally is ensuring a future source of kind of water that is free from pollution and free from disease. So I'm going to put a few slides together on how some nations deal with scarcity, because there's lots of different approaches, and often it depends on how desperate you are and how much money you have as to what your options are. So if you look at Singapore, and I'm sure Katie will correct me here if I'm wrong about this. Is she correct? Oh, good, so far. And so they have this policy to try and be self-sufficient in water by 2061, because they currently, Malaysia is duty bound to sell them about 40% of their water comes from that source, and that will stop in 2061. So they're thinking about what they can do in the future. So this is a kind of top-down policy-led decision that's been made. So what are the things we can do to ensure our security of supply from our own resources going forwards? So they've developed this 4 national taps policies, and there's 4 streams, if you pardon the pun, with 4 different things going into it. So they've reclassified their land, so about 2/3 of the land area has been classified as a protective catchment for the production of water. They've increased the amount of infrastructure, so they've put in more reservoirs for capturing surface water and also more reservoirs for storing treated water, as well as more treatment plants. And they're also delivering new water. I don't know if you've ever had a bottle of new water. So new water is recycled water from the sewage works. It's treated and goes back as water. So I've seen it kind of handed out at conferences and things. So it's quite good to get the students, because it always gets, you're drinking stuff that's been out of the toilet. So it's quite good to get the students to think about that as well, and see what they think. Would they drink it if you brought a bottle in, and would you drink that? See what they would do. And they've also invested heavily in desalination as well. So they've got these kind of 4 approaches to tackling scarcity in their country, mainly because they're able to afford to do that as well. And they've got this big driver, not being reliant on Malaysia in future. Other things you can do is transferring water around. So there's quite a few of these projects now, big, large-scale projects between countries where water is being moved around at huge cost. So this example, this one in China, a 2,400 kilometre network, so a vast network to deliver vast quantities of water. So in order to put this network in, 350,000 people had to be moved from where they lived. So you're thinking about the effects on where that's going, what is the effect of that infrastructure being built there. So there's things to think about there. And also I have concerns about what happens if you're putting all your water resource, you're taking it from one place, you're sending it to another place. There's quite a high potential you're putting a lot of eggs into one basket, because if that becomes unusable because of a massive pollution event or infrastructure damage, then there's a lot of shortfall that you've got to make up from another source. So I am quite wary of these solutions, because I think there's quite a big potential for things to go wrong. And then here's a cost of options that have been looked at in California. So this is just to give you an idea of the relative costs of doing some of these different interventions that we've talked about. So the scale at the bottom, which says cost per cubic metre, that could probably also be switched out with desperation. So basically, as you get more desperate and you've gone to your first ports of call down the bottom, you've got to spend more in order to keep producing the water that you need. So you can see that by far the cheapest options and the most common sense thing to do is be more efficient about what you're doing in the first place. Then we've got groundwater we can look at. So we can drill more wells, we can drill deeper wells, we can improve on what we're doing already to access more of that resource. We can import water, so we've looked at water transfer potentially, or that could also encompass buying in goods that contain embodied water, as we've already seen. And then we've got water recycling, which is expensive because of the range of contaminants you might need to move from it, and the processes are quite energy intensive and costly. Also, you're generating a waste material from that as well, so you've got to think about the cost of that. That's why it's high cost. Seawater desalination as well. So, I mean, California has done all of these things, so where do we go next? If any of your students have great ideas, then obviously if they can think of something along that top line, that's what we want. So I was going to think about links to other themes. So there's a lot talked about the water energy nexus. I don't know if anybody's heard that term, the water energy food nexus as well. So there's a lot of links between, we've talked about agricultural use of water being the highest kind of average global consumption. Thinking now about the kind of next highest, and in some countries it is the predominant use of water, is for power generation. So we're thinking, can a shortage of water make the lights go out? And I believe that water is a bigger threat to our power system vulnerability than actually fuel resource. So there's quite a lot of literature coming out about this at the moment, which is quite interesting. So if we think about kind of global energy mix, 98% of the electricity, so I'm talking all about electricity here, I'm not talking about heat at all, 98% of that comes from either thermoelectric generation, so your standard gas, coal or nuclear power plants, or hydro. So generally, in most places, thermoelectric generation dominates the energy mix for electricity production, apart from in South America, where hydropower is really important. So that in South America, hydropower makes up generally around 68% of their energy mix. So we're heavily reliant on water, whatever we do really, to produce our electricity. And the literature at the moment questions the kind of vulnerability of our current power system globally, and what would be the impacts of climate change going forwards as well. If there was less water around, if there was extreme events, what would be the impacts on that? So the upshot of some of the most recent research says that there will be an impact upon the capacity of our thermoelectric plants and also on our hydro plants. So the thermoelectric plants may not be able to cool as much if water temperatures are higher because of climate change. The hydro, because if rainfall is not as predicted or as has happened previously, then hydro capacity can also drop too. So I've got some examples of this in a bit as well. So I'm just going to do a little bit of a focusing on what's going on in the US. So they are one of the countries where their water consumption for power generation is bigger than their consumption for agriculture. So it's almost half of their water demand is for thermoelectric generation. And these figures here show you the kind of relative water demand. You can see in the kind of greyer, smaller columns that if they think ahead and design their plants better and they recirculate the water that they're using, they can massively reduce the consumption. So if you've got power plants that are kind of located coastally, it's not so bad because you can cool using seawater. Inland, you're either taking from rivers or you're having put in big ponds at the power plant to cool using that. Or you're putting in big air cooling towers, but air cooling you need it quite big to deliver the same amount of cooling that you would from water, because water is such a great medium for transferring heat. So there's something to think about there in terms of how future power plants are designed. They should be designed with future water shortages in mind. And also thinking, well, this might be okay because we're going to have a low carbon transition. We're not going to use coal anymore, and eventually we won't use gas either. But if we switch to nuclear, you can see that nuclear actually uses more water for cooling than either of those as well. So again, it's about thinking about how to design the plants. And the plants that recirculate, that use far less water, still aren't brilliant because that water is kept in ponds for use by the power plants. It's not part of any system apart from that little kind of discrete system surrounding the power plant. Plus there are quite a lot of evaporative losses from the systems as well. So although they're better, they're still not perfect, so there's still issues to think about there. So yes, I think water can make the lights go out. It's happened in Nepal, where around about 30% of their power generation was lost in the recent earthquake. That said, in their population of about 28 million, which is comparable with the state of Texas, I think their power output before the earthquake was 500 megawatts. Texas was 50 times that. So there's also questions to ask the students there about what is power being used for? You know, is it being used for absolutely essential services, or are some uses of power considered profligate, and hence the water that's being used to make the power, should that be used for that purpose? Also, in the heat wave in France, which happened in 2015, their nuclear plant had a lot of problems. Some of it had to be shut down, so they couldn't cool enough with the water resources they had. And they shut down plant, and they also had dispensation to put water into rivers far hotter than it was supposed to be as well. So that has impacts upon the wildlife there as well. There's also another example in Colombia as well. So the impacts of El Nino in Colombia have been to reduce rainfall, which has seriously affected some of their hydro generation, to the point where they're actually reopening mines and bringing coal-fired generation back online as well. So plenty of kind of things to think about, different examples in how a shortage of water can knock on and affect other things. So I was going to finish with a few very quick slides on some of the areas that I'm interested in, which link into all the things I've just talked about. So one of my key interests is geothermal energy, looking at getting heat, mainly heat. So I'm looking at lower temperature. I'm not looking at volcanic stuff. I'm looking at the kind of, I like more of a difficult challenge. So I'm looking at trying to get heat and power from water that isn't boiling, basically. So I'm looking at that. Water, again, is a great carrier for energy. So that's why we're interested in looking at it. It's got great potential in the UK and elsewhere in Europe as well, from relatively low temperature sources. My interest has also been in abandoned mines. And again, we're looking at that. So we're sitting on an area now, part of the Durham coalfield, vastly mined. The whole of the UK, there was 15 billion tonnes came out during the period of mining. You can see how it tailed off. And if you were to get that coal and spread it over the UK, you'd be walking around in about 5 centimetres of it. And that void underground equates to a void that's now filled with water. Admittedly, not all of it, because about half of it is taken up with subsidence. But you can work out how much heat is stored in that water, and it gives enough heat for around about, I think, 750,000 homes. So it's appreciable. The university is looking at it for their buildings. We looked at it on site. So it's taking off as an idea. It's not new. The water there is about 20 degrees, so it's used with a heat pump. But that's one way in which you can make something out of an industrial legacy, which often has a lot of negative things associated with it. The way in which collieries were abandoned almost overnight, people were unemployed almost overnight, everybody was released onto the workforce at once. Then the whole thing was followed up with kind of abandonment, the pollution issues, to actually think about whether we can use some of this infrastructure that was put in for a purpose going forwards. That's something I'm quite interested in. And also on abandoned mines, so metals are one of the biggest threats to wildlife in the UK rivers, according to a recent report for the Centre for Hydrology. So thinking about the impacts that mining has on catchments. In the UK, because of our mines having abandoned, most of our collieries abandoned maybe 10, 15 years ago, we've gone through a bit of a learning curve of how to deal with them, how to treat them. And that is expertise now that I'm interested in using in other countries, both where they're still mining and where they're just about to abandon. Because I think there's things we can offer there. So we're looking at trying to build up some links with other countries doing this. Rivers as well, so we're back in Durham again. So we're thinking of whether we can heat buildings in the Elva area. So just kind of opposite the river more or less from where we are now. Can we heat those using heat from the river? So I've got students going to be looking at that later this year and see what we can do there. And also I mentioned before aquifer storage and recovery. So there's lots of questions to be asked there in terms of research. We've talked about Thames Water have been trialling this as a solution going forwards, but what happens to that water when you put it in? You have to take it out, you have to clean it. How does that work? What's the geochemistry of mixing these two different sources? So there's loads of research questions there. It's used a lot in Australia, so if anybody's interested in looking at it as case studies with the students, there's quite a lot of places there that are using it. Can it be also used to help manage surface water at times of excess? So could it help manage flooding, things like that? So there's lots of things to to think about there. So I'll put some sources together which you'll get when you get the presentation. I'd like to thank you for listening, and I'm aware I've thrown a lot of things there, but I'm happy to take any questions that you have. Thank you.